back? Okay. All right. Thank you, HT, and all of you for inviting me. It's very nice to be here and see so many of my old friends. So I'd like to explain why I'm giving this talk on this topic. One, I think we're all aware that artificial intelligence in some way will play a role in math. One useful metaphor, I think, to think about that is writing. Okay, so if we think about doing, for example, math in our head versus doing math with a pen and paper, those are, in a way, essentially different things. When you have a piece of pen and paper, the paper functions as an external memory, and it also functions as sort of an external part of your brain because you can do computations on it. It's a different type of thinking system. And so that's the, I think a useful metaphor for AI is something that will change the way we think. And if you take that point of view, I think it's not useful to think of it in terms of how we do math. Okay, we might think we're doing math, and how will AI change that? And I think so. There, you kind of conceptualize math as some kind of fixed entity, and then we're doing it, and maybe we'll do more of it. It seems to me that what we'll really do will change the way we think of what mathematics actually is. So the reason I'm giving this talk is I think it's very important. Is this too loud? It sounds too loud to me. All right. Okay. You tell me. So I think we all need to think about that, especially students. And I don't see that discussion really happening. So, if you're a graduate student, this is something that will happen in the course of your career. So what I want to do in this talk is think a little bit and imagine what math looks like as we have more and more ability to do automatic reasoning. Now, it might seem impossible to think about what math will look like, 40 years in the future, because we can't really imagine, I think, what exactly will ChatGPT be able to do or not in 5 years. So my basic point of view on this is always to think about things in human terms. Okay, that is, I have no idea what machines will or will not do in 50 years, but I have a pretty good idea what humans will look like. So I'm going to try to analyze everything in kind of human terms, and correspondingly what will be in this talk is not so much ideas from mathematics proper, but from other fields that have something to say about humanity. So I've cut up the talk into 3 parts just for convenience, labeled past, present, and future. I want to start by talking about some episodes from the history of math which I think are relevant to us, or one episode primarily. And then I'm going to talk about something which I think is not too far from where we are now. What if machines can help us in proving lemmas for us? Okay, maybe not very complicated things, but lemmas. And I want to think through exactly what that means. And then at the end, I'll engage in something which is a bit more like science fiction and think about what it will mean if they can prove things that we can't. All right. So I'm going to start with discussing an episode in the history of math which is called the foundational crisis. I think this is a term that Hermann Weyl introduced. And it refers to the period at the start of the 20th century. There was a great amount of anxiety in the math community, which had built up over the 19th century, because there were worries that what we were doing was maybe had some fundamental problems. Okay, there was this Euclidean geometry had been around for 2,000 years, but then we found there was this non-Euclidean thing, which is sort of disturbing. Our intuition for functions had repeatedly proved to be, let's say at least on shaky ground for the functions that were continuous but not differentiable. And then there were starting to be problems with the way we deal with infinity. Okay, the work of Cantor and set theoretic paradoxes. So all this kind of collectively meant that the mathematical community, I think, was very unsettled. So that period around the start of the 20th century is called the crisis of foundations. And so I'm going to say a couple things about it, but I think actually the name foundational crisis is, although it's commonly used, is maybe the wrong image, because it gives you this image of mathematics being a building, and the building had some cracks, and then we sort of sent some people down to the basement and they filled the cracks, and then we kept going. I think maybe a more useful metaphor is that mathematics is like a person, and the person had a huge anxiety attack. And that person, who's us, we sort of forgot that we had the anxiety attack. But it continues to really shape a lot of the things that we do. Okay, so that's the first reason to study it. I'm actually not going to talk about this so much, but I think we can't really understand why we're doing what we're doing without understanding this crisis and its aftermath. And also, when you look at this, you also come to the realization we might do things differently. Okay, we did things differently before, we can do things differently after. By differently, I mean not only that we might study different problems, but we might, for example, place very different value on proof. Okay, that's a perfectly plausible thing. I'm not going to, this I think is a very interesting thing to think through, but I'm not going to talk about it today. I'm going to talk about two more modest things that are more clearly, I think, related to mechanical math. The first is that it triggered a first wave of interest in what you could call formalization. Okay, and I'm going to show you that in a second. And the second is that it forced mathematicians to confront the ideas of mechanized math. Right? So the ideas of machines doing math was not new even in 1900. Right? So in the 19th century, not only were there mechanical devices to do addition and subtraction, there were mechanical devices that could solve basic logic puzzles. And those devices were thought of by the people who made them as a step towards automatic math. Okay, so it was not a new idea. It was not something. But what this foundational crisis did is it forced mathematicians to actually seriously engage with that idea in some way. Okay, so let us have I'm now going to, oh wait, I'm missing something. Yeah, okay, no. All right, so I think a very important, the eventual response to this foundational crisis was, I think, the adoption of this idea that we can reduce things to axioms and proceed formally, and that will be our way of making mathematics safe. So a very important event here was a book written by Hilbert in 1899, where he wrote down an axiomatic treatment of Euclidean geometry. Okay, he wasn't the first person to do this kind of thing, but he pushed it further, and it was a very influential treatment. And I think the spirit of this book, it's called Foundations of Geometry, is best summarized by this quote that Blumenthal attributed to Hilbert, which is, in place of point, line, plane, we must always be able to say table, chair, beer glass. And whether or not Hilbert actually said that, he certainly said things in the same spirit, so let's just go with it. So I want to unpack what this means, right? The idea is that in dealing with geometry, we were led into error by carelessly using our intuitive notions about lines. Okay, points and lines, we have some intuitive picture of what parallel lines are, and this caused us problems. So as an antidote, we should set up the mathematics in a way that it can be severed from those kind of intuitions about space, which had perhaps were causing us to lead us to be unreliable in our treatment. So Hilbert to set this up entirely from axioms, and what I want to do is look at two different responses to Hilbert's book. Okay, so one was primarily in the United States, and the other one primarily in Europe. So, okay, to set the ground for the first response, let me give you a fun fact. Okay, so here's the fact. If I have a set and it has a operation, binary operation, which I've denoted by dot, and a unary operation, which I've denoted by inverse, and it satisfies this one axiom, then it's a group. Okay? So you can try to prove this. I don't recommend it. This is an example of, all right, so for all x, y, z, and u, if this identity holds, then these two operations define the multiplication and inversion of a group. I'll tell you who proved this a bit later. This is an example of a style of mathematics that became very popular in 1900, which was called at the time postulational analysis. Okay, it was a response to Hilbert's book. People were like, this is great. We're going to axiomatize all manner of mathematical things. So what postulational analysis was they took things like a ring, a field, a group, a Boolean algebra, and then someone would write a paper saying, here are 6 axioms that define them. And then someone else would say, no, here are 5 axioms that define them. And each one, they would painstakingly prove the axioms were independent. Then someone would come up with it. So this one, a group defined in one axiom, that's in the spirit of this postulational analysis. And this was a fairly mainstream thing. One of the most influential figures here was a professor called Edward Huntington, who was a professor of mechanics at Harvard, which is perhaps why I don't know. He seems to be an interesting character, and he's better known for he was one of the inventors of the way that congressional seats are allocated to states. But he did a lot of this postulational analysis. Another person who was doing it was Eliakim Moore at Chicago, who had a huge crop of very influential students, all of whom except for Berkhoff, all of whom were actually involved in this during their students. So this was not some kind of thing relegated to tiny. This was something that mainstream mathematicians were very involved in. Now, I don't know if you can see this. Well, I'll just comment on the relevant. On the left, I think, is a system of 9 postulates for a field, and that's a paper of Dixon. And on the right is a paper of Huntington. The thing, and I don't know if you can see this, but I'll say it. On the left, Dixon, when he's doing his axiomatization of a field, he doesn't use plus and times. Okay, he uses a little circle and a little square. And the reason, which is explained elsewhere, is the same as the spirit of that thing I said attributed to Hilbert. The problem is if you set a plus and a times, we might accidentally use pieces of our intuition about real numbers. And so he's going to use a different notation so that doesn't happen. On the other hand, he doesn't go so far as to write addition as a of xy. Okay, if anyone has ever tried to write arithmetic using addition in that form, you realize it's just completely incomprehensible and completely incommunicable. All right, so there's this weird tension here between the conscious fact that you're going to try to separate yourself from intuition for the purpose of reliability and the fact that at some point that becomes useless to human beings. Okay, so I'm going to say this postulational analysis seems to have died out by about 1940, but it came back a little bit later. I'll say more about it in a second. I'm going to give you the proof of that one axiom definition of group. Okay, now here is a different response to Hilbert. This was from a review that Poincaré wrote of Hilbert's Foundations of Geometry, and it was translated for the bulletin by the same Huntington. So I'm going to quote from the translation. So first he says, we might put the axioms into reasoning apparatus like the logical machine as Jevons and see all geometry come out of it. Okay, so the logical machine of Jevons is what I mentioned. It was effectively a machine to solve logic puzzles that Jevons made in 1870. So Poincaré realizes that if you can set up mathematics in this entirely formal language, it can then be done by machine. So then what does he think about it? He says this idea that we can replace reasoning by formulas seems artificial, puerile, disastrous in teaching, hurtful to the mind, and deadening for originality. So, okay, so Poincaré is not a fan. But he's actually very fair about it. So the last sentence says, as used by Professor Hilbert, it explains and justifies itself if one remembers the end pursued. And so for Poincaré, he was perfectly willing to admit this had a value, but as a means to an end, and that end for him was the human intuition or understanding of math. Okay, it was useful as a support to that, but it was not some kind of path to, let's say, certainty. Okay, and actually, I'm going to say a little more. I think about what Poincaré objected to. So let me quote another thing from this same review. He says about Hilbert's axiomatic treatment, given a sequence of propositions, he puts it in the form where all logically follows from the first. But with the foundation of this first proposition, with its psychological origin, he does not concern himself. So here, first proposition may mean axiom. He's just saying Hilbert reduces everything to some basics. But then he doesn't concern himself with where the basics come from. So the point is, if you set up, you can very well say it in terms of furniture, like tables and chairs. But from that point of view, you cannot understand why the axioms you choose have any sense as opposed to any other axioms, or for that matter, why any of the theorems you prove are more interesting than any others. So the something about Poincaré says there's clearly something about the whole business that depends on the intuitive conception of points and lines, which is not preserved under that transformation. And Poincaré is not the only person to voice that. In fact, this objection was made by many mathematicians. Enriquez addressed it in his talk at the International Congress in 1912. Klein, specifically the idea that there's something of psychological nature that's important in thinking about math. Klein ran an entire seminar about it. And Brouwer, I think Brouwer is sometimes thought of in the context of the foundational crisis. He was someone who proposed a different set of axioms, a different logical foundation for math. But I think that was in a way a reflection of the fact that he was concerned with the same thing as Poincaré, which is to say the psychological origin of what makes mathematics. Okay, so this is a fairly typical quote from Brouwer's early writing. All right, now, in some sense, this point of view was forgotten. That is, the official narrative adopted by math is that we're doing things formally that can be reduced to axioms. But this objection, I think, doesn't really go away. It keeps recurring in different settings. And let me give you an example, which is in the sort of the second life of postulational analysis. Okay, so postulational analysis, as I said, kind of died out, as far as I can see, at least in the 1940s. What made it come back was automated theorem proving. So there was a very, very short time that elapsed between electronic computers and people trying to prove theorems with them. And already in the mid-1950s, parts of Principia had been done by certainly the late 1950s. There were efforts at several places to do theorem proving by electronic computer. And what type of theorems do you try to prove with your electronic computer? The things of postulational analysis were very convenient for this, because they're already in a form that was very close to what you can put into your machine. Now, a point that came up very early in this is the following one. When we render math into sort of formal reasoning, if you and I were to do it, we would take some piece of math and we'd break it up into some small chunks, and the chunks are meant to be so small that each one of them we can just fit into our brain, and each inference fits into our brain. Okay, like our brains are very limited in their ability to hold large chunks of information. And the way we break up math into logical pieces really reflects that. Okay, there's a limit to the complexity of each line, and there's a limit to the complexity of each inference. That's based on, the fact that I have, 3 bits of working memory. Now, this is not necessary if you're going to do proved theorems by machine, right? You can choose equivalent ways, like logically equivalent ways, but the inference rules, the things to go from each line to the next, there's no reason that they should be comprehensible to a human if your goal is to prove. And this was very soon realized and utilized very effectively. So there's a famous paper of John Robinson, which I think the title more or less tells you, a machine-oriented logic based on the resolution principle. This was a paper giving an algorithm to do certain refutations in first-order logic. It was very important in the early history of automated theorem proving. But the important point was, right, that by adopting language that was adapted to machine, it increased the ability to prove things. But the proofs, as you could imagine, become a lot less comprehensible. Okay, so here is, let me show you, this is the proof of that one axiom law for groups. This was proved by William McCoon in 1992, but it was proved by he used an automatic theorem prover called Otter, which was developed at Argonne National Labs. That had been a project for many decades. Let me say, I was about to say you can check each line follows the next, but I have to admit, in about 5 minutes, I was unable to even deduce the second line from the first. Okay, in principle, there's some data on, in principle, oh, bugger, okay. In principle, the thing on the right tells you how to go from the last line, but anyway, without reading the paper, I couldn't even go from the first to the second. Okay, so that's a proof, and there were other proofs, similar proofs that came out of this tradition of a similar character. So maybe the most famous one was a conjecture of Herbert Robbins. So Robbins was an undergraduate student here at Harvard of Huntington and in the 1930s, and he made a conjecture about Boolean algebras that was proved by computer in 1996. Okay, and this made the New York Times. I don't think it had much of an impact in the math community, but again, it was proved by the same program, I think, Otter. And again, I would say in this case, it's even harder to follow the steps. Okay, they all fit on a single sheet of paper. I've put kind of the core of the proof below, but it is not much help to me. So I think what these examples illustrate, at least for me, is that a point that's pretty close to what Poincaré was saying, that even if you have a machine and you want to prove theorems that humans can understand or plausibly be interested in, you can't avoid in some way thinking about human psychology. Okay, like in the space of formally valid statements, there's this incredibly tiny subset which human beings have the ability to understand, which is not reflected in the it's very difficult to understand from any formal aspect. It's really a reflection of how we process it. Okay, so that's I'll stop there talking about the past, and now I want to talk about where we are now. Okay, and to sort of ground where we are now, I'll show you something that was proved the kind of level of a current automatic theorem prover. Okay, so this is a problem here that was on this year's International Math Olympiad. It's to find all positive integers a and b such that, okay, so you take two positive integers a and b and you take the greatest common divisor of a to the n plus b and b to the n plus a. This makes sense for every positive integer n, and you want that to be eventually constant. Okay, you want it to be, for large n, you want it to be independent of n. So this was on the International Math Olympiad, and it was solved by a piece of software that was made by DeepMind called AlphaProof. And okay, what should we note about this? This is not a trivial question. Okay, I'm not saying it's not hard if you're, a number theorist, but it's not trivial. If it was in one of my papers, it would be a lemma. Okay, and I'd spend an hour and I'd prove the lemma, so I wouldn't think of it as a great thing, but it's not a trivial thing. So I think it's not science fiction to imagine some updated version of the software that might actually prove lemmas in a typical current math paper. I'm certainly not saying this software is at that level, but it's in the ballpark. Okay, and of course I don't know what kind of difficulties there are adapting it to the very specialized language of math. But anyway, let's imagine. Okay, so and what I want to imagine that we have this lemma prover. It can't do anything you can't do. Okay, can't do anything fancy. Can't prove anything you really want proven. But what it can do is it can prove the kind of annoying lemmas of which you have a lot in your papers. That thing. And what I want to suggest is that even this lemma prover will really drastically alter both what we do and how we think about mathematics, at least over time. Okay, so this does not have to be something really, it doesn't have to be able to do things that are impossible for us now to make a huge difference. Okay, so let me talk you through some things which I think will happen with this lemma prover. Okay, so the first thing is that some things become easier to do. Okay, there are certain types of math papers where you have lots and lots of these type of little things to surmount, and of course those types of papers will be easier to write, and probably things will become less important for us. Okay, because they've become easier. Probably we'll be able to do more things in certain directions. Maybe that will open up new problems. Anyway, exactly how it works out, the notions of difficulty and importance will change. Okay, the next thing is, of course, our education will start to adapt, because at this point, a lemma is a bit like we'll start to think of it a little bit like a calculation. Okay, like we can all multiply, but most of us are not very good at it because it can be safely outsourced to your calculator. And similarly, you could, at this point, safely outsource various low-level things to your lemma prover. Of course, that changes. I think it really changes how you think of math. If a lot of the way I think of math is based on the fact that when I was a graduate student, there were all manner of things that the only way I could prove it was to know the proof myself. So I had to learn all the low-level details. I think I'd have a pretty different image of what was interesting and important if I were not educated that way. Okay, the next one's maybe a little more interesting. I think some types of mathematics will become obsolete even though they cannot be done by this software. Okay, so for something to become obsolete, it does not need to be doable by means of this lemma prover. The lemma prover just has to provide a more convenient path to the same end. So a typical example of this is if I'm writing a paper, I'm trying to prove something, and I run into something which I can solve by splitting it into 12 cases. Okay, and I do a routine little thing in each case. Now, if that happens to me, I'll usually take the time to try to figure out a smart way to do it so I don't have to write out all 12 cases. Okay? But if I could just plug it into my machine, it's pretty tempting not to bother doing that. I mean, maybe if that's like a major aesthetic thing that I wouldn't do it, but if it's just a tool for something else, I would probably just let my lemma prover handle all 12 cases. So for example, in the theory of compact Lie groups, right, there are 4 families and 5 sporadic cases, and there are all manners of things you could just check case by case. It's actually more enjoyable to check it case by case sometimes. But usually we don't do it that way. That really gives the field a certain flavor. And I think that's partly aesthetics, but also partly that it's the fastest way to do it, which will not be the case. The last thing I want to discuss, but I'm going to discuss this at some length, is the effect of this on the way we conceptualize mathematics. Okay, so to do this, I'm going to go back to this problem that AlphaProof solved, and I'm going to tell you. I'm going to sort of talk through. I looked at this problem, and I'm just going to tell you the first thing I did. Okay, and I'll compare it to what AlphaProof did, and then I want to draw some lessons from that. about how we do math. All right, so here's the problem. You want to find all integers a and b such that the greatest common divisor of a to the n plus b and b to the n plus a is eventually constant. And the answer is a equals b equals 1. Okay? Now, that's the only pair. That's the only solution. Now, so in what follows, let's just assume we know that's the answer, and so we're trying to prove that. Okay, alpha proof did not know that's the answer. It had some auxiliary way of finding the answer, but let's just assume we already know the answer. So, all right, so I'm just telling you literally the sort of how I went about. I just sat down, tried to do this. The first thing I did, is that when you do number theory, one of the most effective tools available to you is to reduce modulo primes. Okay, any problem in number theory, you could usually get somewhere by reducing modulo every prime and seeing what happens. Okay, so that was my first. I'm going to reduce this modulo a prime and look what happens. And how's that going to work? By the way, the details of what follows are not going to be super important. Okay, but I'll just talk you through what I did. So I want to show this GCD is not eventually constant. And so the way I'm going to do that is I'm going to try to find a prime that divides it some of the time, but not for some n, but not for other n. Okay, and then it can't be constant. So the question becomes, when does a prime p divide this greatest common divisor? Okay, so for p to divide a to the n plus b and p to divide b to the n plus a, I just write this in, I work in arithmetic modulo p. So a to the n is equal to minus b and b to the n is equal to minus a. And now in arithmetic modulo p, I can even take logarithms. Okay? So you have to be a bit careful, maybe you have to make sure things aren't 0, but ignoring this, you can take logarithms and you get essentially a pair of linear equations which you can turn into a single quadratic equation for log a and log b. And then you just fiddle with some high school algebra. You find out this has a unique solution if log a times b is log of minus 1. So that's whenever ab is minus 1 mod p. Okay, the only thing that I want you to notice is that the important thing about this is I used this reduction mod p and took logarithms. Okay, and then after this, so you have a problem, because if it has a unique solution, that means that p divides this GCD for some n, but not for other n. Okay, so this leads you to a solution. It's a little bit of a mess to write out because there's some extra case about what happens if p is 2 and so on. But it gives you a solution. And it may be a solution that you could discover for yourself if I told you the general idea. Here's alpha proof's answer. So alpha proof produces a solution in lean. And I'm paraphrasing that. The DeepMind folks could have translated it into a natural language proof. Its proof is very short. Okay, it's much shorter than if I take the essential part of its proof, it's shorter than the one I had. It's easy to check line by line. It's not tremendously clear how it was discovered. It also, in some sense, is doing the same thing as in my proof. Okay, rather than looking at it's sort of like clumping together all the primes at once. It's doing the same thing. It's not an essential. Okay, but the point is, the point I want to emphasize is I used reduction, this idea of I can reduce a question modulo primes, and alpha proof did not. So why did I use that? Okay, so when I say reduction modulo p, right, it's really just a shorthand. Whenever I look at integers modulo p, it's some shorthand for integers which have remainder blah, blah, blah modulo p, and then there are some shorthands about how I can do arithmetic with those things. Okay. But it's a very efficient shorthand, and for two reasons for me. First of all, it's I can use it in many contexts, right? As a number theorist, I don't have to learn a vast variety of tricks specific to different problems. I just remember this one thing. And the second thing is that it behaves like a system that I know very well, which is the real numbers. Okay, if I look at numbers modulo p, I can add them, subtract them, divide them, multiply them. I can even take logarithms, right? So I don't have to relearn a whole bunch of stuff. I can just use basically high school algebra, which is what I did. But those are really, limitations of my mind. I mean, alpha proof certainly doesn't need to optimize either space or time in the same way I do. The fact I use the integers mod p is not because it's some kind of, I think, fundamental thing of math. It's about it because it's efficient for me to think about a certain class of things. So, that's an example of a concept, the integers modulo p. And in math, we use a lot of concepts. Okay, we use so many of them that it's sort of, I think, difficult to imagine that the field could exist without them, right? So things like Hilbert space, category, graph, manifold, differential form, these are all, in the end, okay, they have a definition. They're just an abridgment for some other stuff, but they enable us to think efficiently about that other stuff. Okay, so let me just give you one more example along the same lines. If I take a Hilbert space, imagine you look at a proof in analysis where you use a Hilbert space to prove something about functions. Okay, so you go through this proof, and so what is the Hilbert space doing for you? Maybe there's a function that's close to another function, and f is close to g, g is close to h, then f is close to h. You could, of course, just argue this by hand every time you saw it, but putting it in a Hilbert space gives you a very short way of saying it. Moreover, it gives you a way which is guided by geometric intuition. Okay, it's a very useful fact about the Hilbert space that it is a safe model. The geometry of points in ordinary space is a good model for the Hilbert space. So again, it's relying on something that our brain is good at to think efficiently about an otherwise abstract situation. Okay. So the purpose of these concepts is, going back to what I was saying about proof, our brains are very limited, right? There's a very small number of things we can fit in them in one time, and we use concepts to kind of gather collections of things in such a way that we can fit them into there. Okay, so they make it efficient for us to think, right? So the word that there's a famous 19th century physicist and philosopher, Mach, who described this as economy of thought. Okay, concepts make us able to think efficiently. But so do machines. All right, if I had an argument where I have to keep track of 15 variables, I can do it by packaging a whole bunch of them into a new concept, or I could do it just by telling my lemma prover to handle, that complexity. Right, those are, both reasonable ways of handling that level of complexity. And so if you have a machine, your need for concept changes. Okay, our concepts are based on a certain way of interacting with math, which is not going to be the same. All right, so now I think, it's difficult, as I said, to imagine, like our concepts that we use for math seem like so much a part of reality that it's hard to imagine that we could not use them. Okay, but I think there are many sort of natural experiments you can look at to convince yourself that this is not the case. Right, so those are of the following nature. There are many times when you have, so to speak, the same piece of math that's studied by two different groups of people. And you can look at them and see, did they use the same concepts to represent the same? The same is a maybe tricky notion, but let's say formally equivalent in not too complicated a way pieces of math. And the answer is certainly not. Okay, if you look at how, for example, you can look at how math is done between different fields. If someone who does numerical analysis, if you take a pure math course in linear algebra and compare it with what someone who does numerical linear analysis might learn, right? What we in pure math represent in terms of vector spaces and linear transformations and bilinear structures would be encoded by various types of matrix decompositions. Okay, and those are equal, anything you can prove one way, you can also prove with the other, but they're kind of different encodings of the same mathematical structure, which will make you kind of, I think they suggest different questions, and different things are efficient in one compared to the other. There are lots of examples in the history of math. Okay, there are lots of examples. If you take modern representation theory, there's one part of it that was kind of done in a different way in invariant theory in the 19th century. There's another part of it which is related to the theory of special functions. Those are, again, I'll actually mention both of those in my talk tomorrow. Those are different ways of representing the same math. Okay, and I don't think you can say one is better without having some sense of what the goal is meant to be. With different technologies, okay, you could also, I think, see that math in the era of where we had ready access to computers had a slightly different emphasis on what the useful concepts were as before. So all this is meant to say that I think we can reasonably expect that both the concepts we have will alter a little bit and we'll develop new ones as we were to adapt to machine reasoning, and even not extreme forms of machine reasoning, even something that can, as I said, prove lemmas. Okay, so I don't think I can really say anything useful about what concepts we can use, but what type of concepts will be developed. But I think there's one sort of general observation, which is that when we use a machine to do something, very often the part of the time we used to spend on doing the thing goes into explaining to the machine what we want done. Okay, like I kind of chase around my robot vacuum cleaner, telling it to go in the correct direction. And there's a very nice study by Stephanie Dick of this exact phenomenon in the context of automatic theorem proving. Okay, how the automatic theorem provers shifted the goals of the humans who were interacting with them. So what this suggests to me is that part of at least some new concepts will be adapted for the purpose of helping us communicate with machines that are helping us communicate with these lemma provers. Okay, so what I wanted to suggest here is that even not necessarily profound ability to prove mathematical things would lead us not only to change what we're prioritized, but even change in maybe rather fundamental ways our language. Okay, so now I want to move on to maybe something more like science fiction, which is what if machines can really prove theorems better than we can? Okay, so let me just articulate what the premise is. I want to imagine that if there's a formally stated math question which can be solved by a human, that it can also be solved faster by a machine. For our purposes, it's not important, what exactly I think all I care about is that it's better than humans. I'm also not, I have no idea about if, when this will happen. But I think, even if you think it'll happen in 100 years, it's worth our while to think about it now. Okay, so let me first say some things about this situation that seem unsettling. So first of all, the one role of mathematics is kind of to solve certain types of questions coming from science. Okay, and in this scenario, that is no longer a human activity. Okay, so if it will no longer be the case that a scientist could bring a question to a mathematician, the mathematician would solve it, because the scientist, if still a human, would simply ask his machine to do this task. Okay, so it's not an activity for human mathematicians to be part of that kind of technological role of mathematics dissipates. Secondly, the discovery of proof. So proofs is a kind of complicated word. So here I want to think of a proof as a formal certificate of validity. Okay, there's several things a proof does for us, but for this current purpose, let's just think of a proof as a certificate that something is valid. The discovery of proof will not be a human activity either. Okay, anything that you can prove, your machine can do it faster. There's no need for you to prove it. Now, I'm not, maybe as we saw, right, maybe it can only produce incomprehensible proofs. I think it's actually probably a much more complicated question to produce comprehensible than simply formal proofs. But again, I'm not going to take a position on that, right? Whether or not, I think in this situation, even if such a machine produced largely incomprehensible proofs, I would imagine that we would place much less value on proofs as a goal of math. Okay, so at least I do not think that in this situation, I don't think human beings will stop doing mathematics. Okay, I'm not saying there'll be jobs for them, but I don't think we'll stop doing math. But at this point, you have to start to wonder what I actually mean by that, right? If something, how are we to know if this activity looks very different from us? What makes it mathematics? So the question of defining mathematics, I think, is a very difficult one that many philosophers have attempted answers. I don't think there's a satisfactory one, but I'm going to give you what we might call a description of mathematics that I think is useful for the current purpose. Okay, it's a very nice description. I think more mathematicians should know it, and it's due to Philip Davis and Reuben Hirsch. They say that mathematics is the study of mental objects with reproducible properties. Okay, so I'm going to first spell out what this means, and then I'll say why I think it's a useful description in the context of thinking about automatic reasoning. So, all right, here's what I understand them to mean. So if I describe to you the concept of a right angle, now probably most of you know what a right angle is, but if you didn't, so I described to you the concept of a right angle, you might forget that concept, but I think it's unlikely you would remember it slightly wrong. Okay, it's a kind of rigid concept. You can forget it, but if you remember it, you'll remember exactly the same concept I have. You could tell your friend, and then they would tell it to me, and I would agree, yes, that was my concept of a right angle. Okay, and that way it differs from natural language. All right, like any word of natural language has a certain ambiguity, which does not. So it doesn't. Natural language doesn't have this rigidity. And the reason I think this is a valuable definition is that there are two reasons. First of all, in line with what I said as the policy of the talk, it defines mathematics as a human activity, okay? Because mental objects are these are objects of human thought. And the second point is it also defines it more or less as a social activity, right? Because the question of something being reproducible is something about, can you reproduce this mental object in somebody else's mind? Okay, so I think it's a nice definition, and I want to talk through why, so what is the value of mental objects with reproducible properties? Okay. So I'm going to give 4 points which I think are a value of them even in a world where you have AIs that can do all manner of things for you. So the first is psychological certainty. Okay, and by psychological certainty, I don't mean proof in the mathematical sense. Okay, I mean the kind of thing you might bet your life on. Now, if I wouldn't bet my life on one of my proofs because I wouldn't be here if I did. But if you look at the proof that an isosceles triangle is, if it has 2 equal sides and has 2 equal angles, right? That proof, you can just grasp the whole thing and you're completely certain it's true. So I think that's like a rather amazing thing that one can have this kind of psychological certainty, and I think people have always been captivated by it. Okay, I think that's why Jefferson and Lincoln enjoyed reading Euclid, is that this idea of having psychological certainty about something in the outside world. Okay, then the next is exactness of communication. So, many of the ways that we, you need to communicate exactly, you need to have some kind of mental structure that's held in common. When we, for example, use numbers to in a financial transaction, the point of using numbers is not that the thing is intrinsically numerical, but that the numbers mean exactly the same thing to all the parties involved. Okay, so the numbers are really serving a social function. They're not about the world, but they're about how we are aligning our minds with each other. Okay, the third point is scientific understanding. Right? So the word reproducibility already suggests, if you think of science as about reproducible properties of the natural world, it's reasonable that any mental model of them should be reproducible. And I think this is, again, something which has nothing to do with technology. The people have always been interested in understanding the world, why do planets go in closed orbits, things like that, and I think they'll still be interested in that, and it's impossible to do that without mathematics in this sense. And the last is aesthetic satisfaction. I think, of course, this is why most of us do it as mathematicians, but I think we maybe underestimate the amount that non-mathematicians are willing to credit that mathematics can have an aesthetic component. So, I think I can sort of plausibly imagine a future mathematics which we think of as the study of reproducible mental objects. Okay, I think it would have some overlap with what we do now, but also would involve a broader range of inquiry. Let me say actually something that I hope we might understand in this future study of reproducible mental objects. For me, the most interesting feature of the math I've encountered is the convergence between different subfields that were apparently studying different things, right? So in 1880, Dedekind and Weber found that Riemann surfaces were they found this analogy between Riemann surfaces and number fields, right? And then in 1960, Barry Mazur, who isn't here today, realized that could be upgraded to an analogy between three manifolds and number fields. And then in the early 2000s, it was discovered that under that analogy, the Langlands program behaves like a topological quantum field theory. So analogies like that seem so improbable. There's a philosopher, David Corfield, who has a joke. He calls it the unreasonable effectiveness of mathematics in mathematics. So they seem so incredibly improbable that they demand some explanation, right? And I think that's really so that's something which we might find not as being about mathematics, but really about our minds. But anyway, that's the kind of thing that we might learn. Okay, so yeah, good. So let me just summarize what I've said. I think what I've tried to say is that the future version of math looks, to me, likely to be so different from what we do now that we really need to renegotiate the basic goals of, okay, we have to look at what we're doing and why, and possibly rethink a lot of it. And the other point I tried to make here is that there are many ideas from history, philosophy, and psychology which I think will be useful in that process. So the last point I wanted to say is that, one thing that we could do, this is of course a big, huge thing to think about, but I think a simple thing we could start to do is value communication much more. So we are very bad, pure mathematicians, at communicating even to people outside our narrow subfields. Okay, like most of the time I'll go to a seminar and clearly 3/4 of the audience is lost. And I think this is partly because we have highly specialized languages, but it's partly because I think we haven't placed enough emphasis on thinking about why we're doing what we're doing. Right? And so I think just in the process of learning to communicate better, will put us in the right mental frame for having this larger discussion of where the subject is going. All right, thank you for listening.